In this video, we will look at integrals of all 6 trigonometric functions, and then we will look at some examples. So from derivatives, d by dx of sine x equals cosine x, and negative sine x, we already know that integral of cosine x will look like sine x plus constant. And from this one, we know that the integral of sine x will be negative cosine x plus constant. So in this video, we will look at how we can derive integrals of tangent, then secant, cosecant, and cotangent, so that we have integrals of all 6 trigonometric functions. All right, here I have listed integrals of all 6 trigonometric functions. I have also included sine x and cosine x, which we already talked about, so that we have all 6 together. So we know integral of sine x is negative cosine x plus constant, and integral of cosine x is sine x plus constant. So we already got these two. Now we want to try to find integrals of tangent, cotangent, secant, and cosecant. So let's look at integral of tangent. First, we want to write tangent as ratio of sine over cosine using the cosine trig identity. And then we can use u substitution over here. So we can let u to be cosine x. Now we want to express dx in terms of du. So for that, we'll have to find the derivative du over dx. So this becomes negative sine x, derivative is negative sine x, which implies dx is simply du over negative sine x. So now we are ready to write this integral in terms of u. So this becomes integral sine x over u times dx is du over negative sine x. Looks like sine x gets canceled out. So we are left with negative 1 over u du. We know that the integral of 1 over u is natural log of absolute value of u. So this becomes negative natural log of u. But we know u is cosine of x. So natural log of absolute value of cosine of x plus constant. And I should put that plus constant here also. So this is the integral of tangent. So antiderivative of tangent of x is negative natural log of absolute value of cosine of x plus constant. Next, let's look at cotangent. Again, we can write integral of cotangent of x as integral of cosine of x over sine of x, because cotangent of x is simply cosine of x over sine of x. Now we can let u to be sine of x. Then we want to write everything in terms of u, including dx. So to write dx in terms of du, we can find the derivative of u, du by dx, and that will be cosine of x. So this simply implies dx equals du over cosine of x. Then we are ready to write this integral in terms of u. I'm going to keep cosine of x as it is. In the denominator, we have sine x, which we replace by u. And then dx is du over cosine of x. So now looks like cosine x gets cancelled out very nicely. Then all we are left with is integral of 1 over u du. And we know that the integral of 1 over u is natural log of absolute value of u plus constant. Now we can replace the expression for u back. So we get natural log of sine x plus constant. So this is the antiderivative of cotangent of x. Next, let's look at secant of x. So for this one, we will multiply the top and bottom by secant x plus tangent x. And then we will let u equals secant x plus tangent x. So this is one of the tricks to find integral of secant x. So we get du over dx equals integral of secant x is secant x tangent x plus integral of tangent x is secant square x, which is simply secant x times tangent x plus secant x. So therefore, from here we see that dx equals du divided by secant x tangent x plus secant x. So now we are ready to write this integral in terms of u. So we get secant x plus tangent x here divided by u, because we are letting everything in the denominator to be u, times dx is simply du divided by secant x tangent x plus secant x. Looks like this whole expression secant x times secant x plus tangent x is exactly same as what we have here. So that goes away. Then we are left with integral of 1 over u du, which is simply absolute value of u plus constant, but our u is secant x plus tangent x. So this is absolute value of secant x plus tangent x plus constant. So this is the antiderivative of secant of x. Okay, the last one here, cosecant of x. So using the similar idea as we did with secant x, here we'll multiply top and bottom by cosecant x plus cotangent of x. So that will give us cosecant x times cosecant x plus cotangent x divided by cosecant x plus cotangent x dx. So now we will let u to be the denominator part here, cosecant x plus cotangent x. Then since we want to write dx in terms of du, we have du over dx equals derivative of cosecant x, which is negative cotangent of x cosecant of x plus derivative of cotangent of x, which is negative cosecant square of x. So this gives the derivative of u with respect to x equals, I can simply factor out negative cosecant of x, then we get cotangent of x plus cosecant of x. So therefore, from here we see that dx equals du over negative cosecant of x, cotangent of x plus cosecant of x. So therefore, this integral becomes, so on the top we have cosecant of x plus cotangent of x divided by u, since we let this denominator part to be u, times we have du divided by negative cosecant of x times cotangent of x plus cosecant of x. So luckily, this is exactly the same as that. So we can cancel that out. And we get negative 1 over u du. But we know the antiderivative of 1 over u is absolute value of natural log of u plus constant. And we know that u is cosecant x plus cotangent x. So we just put that expression back here. So cosecant x plus cotangent x plus constant. This is the antiderivative of cosecant. So we derived the formulas for antiderivative of all 6 trigonometric functions. Right? And these are the formulas we just derived. Next, we will look at some examples using these formulas. Okay, the first one, we are looking at integral of theta tangent to theta square. If this looks confusing, I can put parentheses like that over here. So tangent of 2 theta square with respect to theta. So we start by letting u equals 2 theta square, which is the inside part of this composition. So 2 theta square. And then we want to express the integral in terms of u. So we want to express d theta in terms of du. For that, we find the derivative of u with respect to theta, which will give us 4 theta. So this implies that d theta equals du over 4 theta. So therefore, this integral becomes, I'm going to write theta as it is. Then we have tangent of u, since we are letting 2 theta squared to be u. And d theta is du over 4 theta. So it looks like theta goes away. So we are left with 1/4 integral of tangent of u du. Now we look at the formulas. So we can apply this formula over here. And that will give us 1/4 natural log of cosine of u. Applying this formula exactly. Now we can put down what u is. So this will look like 1/4 natural log of cosine of u is 2 theta squared plus constant. So this is the integral. Okay, let's look at the next example. So here we are looking at antiderivative of cosecant square of t over cotangent of t. Since cosecant square of t is derivative of cotangent of t, we will let u to be cotangent of t. Then we want to express dt in terms of du. That means we need to find du by dt. So derivative of cotangent of t is negative cosecant square of t. That means dt is going to be simply du divided by negative cosecant square of t. So now we are ready to write this integral in terms of u. It becomes integral of, I'm going to write cosecant square of t as it is, divided by cotangent of t is u. We are letting that to be u. And dt is du over negative cosecant square of t. Now we can cancel out cosecant square of t. So that will give us negative 1 over u du. And we know integral of 1 over u is simply natural log of absolute value of u plus constant. And finally, we can put the expression for u back. So we get cotangent of t plus constant. This is the antiderivative of this function. This is the next example we have. Here we are trying to find integral of secant of x over 2 with respect to x. So we start by letting u equals x over 2. And we want to express dx in terms of du. For that, we need to find du by dx. That will be simply 1/2. So this implies dx equals 2 du. Now we are ready to write this in terms of u. So this becomes integral secant of u, and dx we found that to be 2 du. I can pull that 2 out and write this as secant of u du. Now looking at the formulas, secant of x, integral of secant of x is natural log of absolute value of secant of x. We have u instead of x plus tangent of u plus constant. And then finally, we can replace the expression for u back. So we have secant of x over 2 plus tangent of x over 2 plus constant. This is the antiderivative of this function of secant of x by 2.